Welcome to second session of the 18th May coaching series UGC Net Statistics Design of Experiments. Here in the session 1 we learned about the basic analysis of variance, one way, two-way analysis of variance. Here there we established fundamental mechanics of various decompositions via analysis of variance. Here we bridge the theory into practice by exploring how experiments are structurally built. We will cover core definitions, master Fisher three basic principles of experiments, the and dissect the layouts, analytics, and relative efficiency of CRD and randomized block designs. The basic terminology, principles of design of experiments, and CRD, RBD, advantages and disadvantages of CRD and RBD. We will discuss now. Now, our precise objective for this session is to learn the basic terminology of experimental design. Before going to the design of experiments, the basic terminology and unpack the fundamental principles of design of experiments, step through both CRD and RBD structures. Here, what exactly is the design of experiments? R.A. Fisher beautifully designed, beautifully explained, defined it as it is a logical construction of an experiment in which the degree of uncertainty with which the inference is drawn may be well defined. Similarly, a poorly designed experiment will yield massive data that no advanced statistical method can be rescued. A well planned design involves managing your experimental layout, ensuring systematic information collection, formatting robust statistical hypothesis, and tailoring your exact analysis strictly beforehand to minimize basis and boost precision. Here, any design of experiments can involve the planning, obtaining relevant information, formulating statistical hypothesis, statistical analysis of the data. It provides more accurate and fruitful results. Suppose an experiment is conducted to examine the effect of three different drugs administered to 5 patients. The experimenter must decide selection of the suitable patients, climatic or environmental conditions, quantity of drug to be administered, method of measurement, proper statistical hypothesis. Efficient planning helps in obtaining valid statistical inferences. The definition is it is a logical construction of an experiment in which the degree of uncertainty with which the inference is drawn may be well defined. The design of experiments provides a systematic method for conducting experiment scientifically. In agricultural research, different fertilizers are applied to crop fields. Experimental conditions are carefully controlled. Yields data are collected systematically. Statistical analysis planned to compare fertilizers. A proper experimental design helps in reducing the bias and improving precision of conclusions. Let us look into the basic terminology. Various objectives of comparison in the comparative experiment is called treatments or varieties. These are the objects of comparison under study, such as different fertilizers in agriculture, different drugs in medical trials, different fields in animal husbandry, different teaching methods in education, etc. The most important points is the main source of comparison is treatment series. It helps identify best alternatives. Central objective of the experimentation is the treatment or variety. We need to take some precautions while choosing the treatments. The treatment should be clearly distinguishable. Number of treatments should not be too large. Treatment should be particularly meaningful, and experimental conditions should be same for all the treatments. Bias must be avoided. Here we have fertilizer A, fertilizer B, fertilizer C. These three are the treatments we are applying for a paddy. Next definition is experimental unit. This is the smallest division of experimental material which treatment can be applied. A small plot or a land, an individual animal, a patient in clinical trials, a student in educational studies. Why this experimental unit is important? It is the basic observational unit. It determines the sample size, affects experimental accuracy. The precautions must be: unit should be homogeneous, must be independent, proper size should be maintained, environmental variation should be minimized, equal opportunity for all treatment should be given. These are the plots. Plot 1, plot. These are the experimental units. Next is blocks. To control variability, experimental material is divided into homogeneous subgroups, homogeneous stratums in sampling. The homogeneous subgroups are called blocks. Within the blocks, there must be homogeneity, and between the blocks, there must be heterogeneity. Same fertility land plots, same age group of animals, same background of students are the examples. It reduces experimental error. It increases precision. Blocking increases precision. It controls nuisance variations. Some precautions are: units within the blocks are homogeneous. They differ from one another. Proper blocking criterion is essential. What is the blocking criterion? We are adopting is the important. Too many blocks should be avoided. If block size increases, which the treatments must be increases, the replications must be increases. Block 1, as much as homogeneous within the block. Block 1 is all the same type of same category of items. Block 2, block 3. Next one is experimental error. The variation due to chance causes is called experimental error. If we apply the treatment, same treatment is applied to several homogeneous plots, still yields may differ because of the uncontrollable factors. The central concept behind the ANOVA is to reduce the experimental error. It determines the reliability of conclusions. Smaller error gives better precision. Which causes experimental error? There may be soil variation, the measurmental error, environmental fluctuations, human handling differences, instrumental errors. We should take some precautions before to control experimental error. Use homogeneous units as much as possible. Apply proper randomization. Increase replications. Control environmental factors. Next is precisions. Here, the core objective is to maximize precision. Precision is mathematically defined as the reciprocal of the variance of the mean. If the experiment is replicated r times, we write p is equal to 1 by variance of y bar. This is nothing but 1 by sigma square by r. Here r is equal to number of replications. This is equal to r by sigma square, where sigma square is the error variance. High precision means smaller experimental error. To increase precision, we need to increase replications, which leads to cost. To increase the precision, we must reduce experimental error by replicating more replications, by using more replications. Use proper blocking. Blocking also increases precision. To improve measurement techniques, use homogeneous units. This is, if we increase replications, precisions must be increasing. Relationship among experimental terms. Here, the treatments, experimental units are main causes for experimental error. Experimental error leads to, by reducing the experimental error, we can increase our precision. Our main objective of design of experiments is minimize experimental error and maximize precision. Better design, better inference, better decisions. Next is the basic principles of experimental designs. In order to compare the effects of several treatments, we conduct an experiment. The efficient experiment should provide experimental error is which is valid, experimental error which is minimum, precise estimates of treatment effects, and reliable statistical conclusions. To achieve these objectives, Professor R.A. Fisher suggested the three basic principles of experimental design. They are fundamental principles of experimental design. They are replication, randomization, local control. Initially, the meaning of replication is repetition of treatments uh, on experimental units repeatedly. Replication. It is this critically, replication serves two primary functions in an experiment. First, it provides a valid estimate of the experimental error variance. Without replication, we should not get the variance. It helps to perform analysis of variance. It reduces experimental error. It increases precision of estimates. It involves efficiency of the design. From sampling theory, variance of y bar is equal to sigma square by n. If treatment is replicated r times, variance of y bar is equal to sigma square by r, where p is equal to r by sigma square. Optimum number of replications. Precision increases with replication. More replications reduce variance. Valid estimate of error is obtained. The general rule is number of replications should not be less than 4. Minimum, there should be 4 replications. Error degrees of freedom should be preferably at least 12. Suppose 4 fertilizers are tested on 20 plots. If each fertilizer is applied to 5 plots, or should be 5, hence better precision is achieved. It eliminates personal human bias, prevents systematic environmental variations from favoring one specific treatment, and guarantees that our error terms remain independent and identically distributed. Next is randomization. Allotment of treatments to the experimental units with equal probability is called randomization. Every treatment should be equal chance of being allotted to any unit. We can adopt any of the following methods for achieving the randomization. Lottery method. Randomly, by using the lottery method, we can allot the experimental units or the treatments. We can allot the treatments to the experimental units. Random number table, computer randomization. It removes personal bias. It makes experimental error unbiased. Randomization ensures independence of errors, validates statistical tests. Without randomization, systematic bias occurs, adjacent units become uncorrelated, become correlated, errors may not remain independent, statistical tests become not valid. Suppose 3 fertilizers we have A, B, C. If we allot the plots A, B, B, C, C, it is not the random allotment. Randomization procedure is this is the randomization procedure. First allot B, next C, next A, next C, next B, last A. These ABC are randomly allotted, which is replicated 2 times each treatment. This avoids personal bias. So, the last principle of experimental designs is local control. It is the process of reducing experimental error by dividing heterogeneous experimental material into homogeneous blocks. The procedure is divide experimental units into homogeneous groups. Groups are called blocks or stratum. Treatments are randomized within each block. It reduces experimental error, increases precision. It improves efficiency of the design. Think it this way: if a field has a clear soil fertility gradient, neighboring plots will naturally be far more homogeneous than distinct plots. By grouping adjacent plots into a block, we ensure that the large fertility differences between blocks can be measured and statistically subtracted out from our final error term. This leaves us a this leaves us with a distinctly reduced, highly precise error variance. Examples of local control are land divided according to the soil fertility, animals grouped by breed or age, students grouped by intelligence levels. This is the local control technique. It is reducing the experimental error by grouping them into their characteristic. Neighboring plots are more homogeneous than distant plots. This is the key table where the different design of experiments, what are the principles used, you must carefully remember it. In both the three all these basic 3 designs uses replication principles, whereas the CRD principle is not using local control. Replication, randomization, 2 principles of experimental units, 2 principles are only used. In RBD, replication used, randomization within the blocks, local control blocks introduced. Whereas in LSD, replication used, restricted randomization, both rows and columns controlled. CRD is the simplest design. RBD controls one source of variation, whereas LSD controls two sources, or within the rows and within the columns. Better control of variation is the smaller error. Next one is we switch into comparison table of RBD and LSD. This is the very important source bank of your questions. Here CRD is completely randomized design, full form, randomized block design, Latin square design. Homogeneity in all the experimental units are homogeneous in CRD. In RBD, homogeneity is within the blocks. In LSD, within rows and within columns. Here, blocking concept is absent in CRD. Blocking concept enters in RBD only one way. Blocking concept is in two way in Latin square design. Here, it is completely randomized design, randomization complete. Here, randomization is within the blocks. Here, randomization in LSD, it is restricted. Complexity, CRD is simple. Complexity is moderate in RBD. In LSD, it is high. The precision is low in CRD, moderate in RBD, high in LSD. Experimental error is large, and in RBD it is reduced. In LSD it is minimum. Suitable for CRD is suitable for homogeneous units, laboratory experiments. All the units must be homogeneous only. In RBD, one source of variation is there in the data. It is suitable for RBD is suitable. Whereas in LSD, we can test two sources of variation. Replication, randomization, local control gives us minimum experimental error, maximizes our precision. The main objectives is obtain unbiased estimates, reduced variability, improve reliability of conclusions, increase efficiency of decision. What is the main objectives for these three principles? Ensures validity of statistical inference. Good design gives us good analysis, makes good decisions. Importance of Fisher principles: reduce experimental error, increase precision, remove personal bias, ensure validity of statistical tests, improve efficiency of design. We have covered all this. This is the quick review of what we learned so far: randomization, replication, local control. Randomization, allocation of treatment. Random allocation is randomization, removes bias, validates statistical inferences. Repetition of treatments helps estimates experimental error, improves precision is the replication. Local control controls variation, uses homogeneous groups, increase efficiency. Let us move into the completely randomized design. It is the simplest of all experimental designs. Layout and analysis of CRD is simpler compared to other designs. It is based on the principles replication and randomization. The treatments are allocated completely at random to all experimental units. No blocking or grouping. Experimental units assumed homogeneous. Replications may be equal or unequal. Simplicity designed to implement. Ungrouped, it is also called ungrouped randomized design. The applications are, as early I told you, it is limited to laboratory experiments, greenhouse studies. Controlled environmental studies, we can use the completely randomized design. Layout of the completely randomized design. Suppose we have K treatments under consideration. Similar to the one-way classification, I is equal to 1 to K Ri. Ri is the replication, number of replications. Total must be equal to N. Total number of experimental units N. Treatments are allotted completely at random using whether lottery method or random numbers method or computer randomization. Suppose we have k is equal to 4, r is equal to 4, total experimental units is 16. Here these 16 units, 4 treatments A, B, C, D, by using the random numbers or lottery method, we allot this way. Here we have 16 experimental units. Each treatment is randomly distributed among experimental units. Alternative layouts. This is layout 1. Here the treatments are assigned randomly to the units. No restrictions are imposed on allocation. This is the another layout. Different random arrangements are possible. Randomization eliminates personal bias and ensures unbiased experimental error. Advantages of CRD: it is simplest one, it is easy to understand, easy to analyze, ensure experimental is fully utilized, provides maximum degrees of freedom for error sum of squares, which leads to the type 1 error and less precision. Error variance decreases due to larger error degrees of freedom. Completely flexible regarding number of replications. There is no there is no restriction on replications. Missing observations can be handled easily. Simply remove them. We can continue our experiment. Most useful in laboratory experiments. Suitable when experimental material is used homogeneous. Computational procedures are also simple. Different treatments can be replicated in different number of times. Major disadvantages of CRD is it is suitable only when units are homogeneous. Efficiency decreases when heterogeneity involves. We cannot find homogeneous units, homogeneous material everywhere. Heterogeneity is unavoidable. Local control principle is not at all used. Relative efficiency is less compared to RBD and LSD. Additional limitations is not suitable for large field experiments. It is limited for laboratory and greenhouse effects models only. Soil fertility variation cannot be controlled. Experimental error may be large. Precision becomes low under heterogeneous conditions. It is best for homogeneous experimental material and small controlled experiments. Let us summarize the CRD: simplest, suitable for homogeneous material. Simple layout, flexible number of treatments, easy analysis, less efficient for heterogeneous material. Experimental error may increase. This is the simplest one. Treatments assigned completely at random, no blocking concept, suitable for further, suitable for homogeneous material. Number of replications may be equal or unequal. The error degrees of freedom is equal to n minus t. Treatments are allocated entirely at random. This is the ANAVA table for CRD, similar to one-way classified data. If suppose we have 3 treatments, t minus 1 is the treatment degrees of freedom, error minus t, as we discussed earlier. Total is equal to n minus 1. Sum of squares due to treatments, error sum of squares, total sum of squares, mean sum of squares due to treatments, mean sum of squares due to error. F is equal to mean sum of squares due to treatments divided by mean sum of squares due to error. Need for randomized block design, RBD. If experimental units are completely homogeneous, we prefer CRD. In practice, complete homogeneity is not at all possible. When the number of treatments is large, experimental area is large, soil fertility varies, environmental conditions differ. Under such conditions, CRD provides large experimental error, which leads to reduces efficiency and precision. To reduce experimental error caused by heterogeneity, Fisher suggested the principle local control. This principle leads to the development of randomized block design. Our main objective of randomized block design is to reduce experimental error and to increase precision. If the variability is due to one major factor, the experimental units are grouped into homogeneous blocks. The important features of RBD is units within blocks are homogeneous, between blocks are heterogeneous, treatments are randomized within each block. The number of units in each block equal to the number of treatments. Here the restriction enters. Number of blocks equal to the number of replication. It is an experimental design in which experimental units are divided into homogeneous blocks. Treatments are allocated randomly within the each block. Number of blocks should be at least greater than 2. Suppose we have K treatments, or now 4 treatment we have, suppose K is equal to 5 and R is equal to 4, the treatments A, B, C, D, E. Suppose R is equal to replications. This is the layout of randomized block design with K is equal to 5. K is the varieties. Each variety is replicated 4 times. There are 5 varieties replicated 4 times. 5 into 4 is equal to 20 plots, 20 experimental units we have. Each block contains all treatments exactly once. Here this is the block 1. Look here, A one comes once, A, B, C, D, E. No repetition of treatments, no repetition of treatments in the blocks. Only 4 blocks we have. We divide the entire experimental units into 4 homogeneous subgroups blocks. Within each block, we apply treatments equally. Each block contains all treatments exactly once. Randomization is performed independently within each block. Here, alternative representation of RBD. Here, block wise. This is the block. Here it is in row wise. Here it is in row wise. Here it is in column wise. Each column represents a block. Important characteristics: one source of heterogeneity control, local control principle applied, experimental error considerably reduced, precision higher than CRD, hence RBD is more efficient than CRD. The advantages is its statistical analysis is also simple and easy. Heterogeneity is controlled using local control. Experimental error is considerably reduced. Number of blocks can be increased or decreased easily. RBD is more efficient than CRD. Extensively used for scientific experiments. Precision is higher compared to CRD. RBD is suitable for agricultural field experiments. It provides valid and reliable conditions. Main strength is reduction of experimental error. There are some limitations to RBD also. It is not suitable when number of treatments is large. Large number of treatments requires large block size. Large blocks may not remain homogeneous. Unequal replications are not possible. Missing observations complete complicate analysis. Two-way heterogeneity cannot be controlled. Layout becomes difficult for many treatments. RBD is most suitable when one major source of variation exists. Blocks can be formed homogeneously. This is the conclusion. Number of treatments is moderate. Let us summarize the RBD. Experimental units are grouped into blocks. Each block contains all treatments, reduces experimental error. Experimental units are grouped into homogeneous blocks. This is again repetitions. Control block to block variation. Error degrees of freedom is equal to B minus 1. B is the block, T is the treatment. B minus 1 into T minus 1. This is an example for a block or a layout of randomized block design. Here we have 4 plots, 3 blocks, 3 homogeneous groups. Each treatment appears only once in every block. Better precision controls block variation, widely used in agriculture, not suitable for many treatments. Missing observations is complicate analysis. Here, the relative efficiency of RBD over CRD is: if variability in experimental units is due to only one major factor, then it can be controlled by the principle of local control using RBD. The gain obtained due to blocking is measured by comparing the precisions of RBD, CRD. Suppose K is equal to number of treatments, R is replicates, total number of units is KR. Let Sigma square R is the error mean summa square of RBD. Sigma square C is the error mean summa squares of CRD. The relative efficiency of RBD over CRD is given by 1 by sigma square R by 1 by sigma square C, which gives us sigma square C by sigma square R. Here C is the error means summa squares due to CRD. This is due to RBD. This relative efficiency is generally expressed as percentages. According to Yates, if relative efficiency is greater than 75%, it indicates a good efficiency of RBD over CRD. Here, ANOVA table used relative efficiency treatments K minus 1, Q1, M1 is equal to Q1 by K minus 1. Here M2 is equal to Q2 by R minus 1. Sigma square R, RBD, Q3 by K minus 1 into R minus 1. Important find, RBD experiment without blocks become CRD. Here, this is the error variation in CRD is estimated from RBD as sigma square C is equal to R minus 1 into M2 plus R into K minus 1 into sigma square R by KR minus 1, where M2 is the mean sum of squares due to blocks. Since R minus 1 M2 is equal to Q2, we get RC is equal to Q2 plus R into K minus 1 sigma square R by KR minus 1. The interpretation is if blocking effect is large, Q2 become large, hence sigma square C is greater than sigma square R. Therefore, RE is equal to sigma square C by sigma square R becomes greater than 1. Thus, RBD becomes more efficient than CRD. Error degrees of freedom comparison. Error degrees of freedom in CRD is equal to error degrees of freedom in RBD plus treatment degrees of freedom in RBD. Therefore, we have blocking in RBD removes block variation from error variation, hence error variation decreases and precision in RBD. Smaller error variance leads to higher precision. In case RE greater than 1, RBD is more efficient than CRD. In case RE is equal to 1, both designs are equally efficient. In case RE less than 1, CRD is more efficient. Why RBD usually perform better? It controls heterogeneity, it uses local control, it removes block variation, reduces experimental error, improves precision. When experimental material is heterogeneous in one direction, RBD is preferred over CRD. The net important areas is principles of design of experiments, CRD versus RBD, ANOVA tables, merits and demerits. The session summary is basic terminology, design of experiments principles, CRD, RBD, missing plot is next session, exam oriented preparation, previous UGC net MCQs, formula shortcuts, CRD, RBD comparison, randomization, replication, local control, randomization removes bias, replication ensures error, estimates error, local control reduce variability. It is the previous question. Local control in experimental error is meant to increase efficiency, reduce experimental error, form homogeneous blocks. Answer is all of the above. Important concept is replication means repetition of treatments. Advantages, estimates experimental error, improves precision, increase reliability. This R is equal to 2 d square alpha s square by d square. Number of replications depends on precision required, experimental material, heterogeneity, all of the above. Answer is 4. CRD is the simplest one. This is the mathematical model for CRD, suitable for homogeneous material, one-way classification, random allocation of treatments. This is the ANOVA table. If numerical question, total degrees of freedom is 9 and treatment degrees of freedom is 4. Error degrees of freedom is equal to total minus treatments is 5. Sum of squares in RBD compared to CRD is sum of squares in RBD, CRD less. CRD is suitable for homogeneous material 2. Randomized block design. About this is the summary of randomized block design. Grouped into blocks. Each block contains all treatments, controls variation, block variation more efficient than CRD. This is the ANOVA table. Error degrees of freedom. Missing plot technique. This is x is equal to b, small b is number of blocks, b dash is equal to given total total blocks given that block only. This is the block total, treatment total, grant total. Given values. These are the dash is given values. The missing value in RBD estimated by minimizing error mean sum of square. This is very important. This is the important table examination point of view. Here the feature is experimental units is homogeneous in CRD, heterogeneous in RBD. Classification one way, here in RBD it is two way. Precision is less, more. Blocking, there is no blocking in CRD, yes. Error variation is higher, lower. RBD is generally more efficient than CRD. In RBD, blocks are formed perpendicular to fertility gradient. Randomized block design is one restriction design, whereas LSD is two restriction design. CRD homogeneous material, RBD blocking concept, error degrees of freedom b minus 1 into t minus 1, precision greater than. Here principles of DOE, replication formula, CRD model and ANOVA, RBD model and ANOVA, missing plot estimation, error degrees of freedom, efficiency of designs, block formation concepts. Practice numerical problems daily. You will get the success. Thank you.